Now that we've learned how to find derivatives and antiderivatives of the inverse trig functions, I thought I would show you two useful integrals, useful in the sense that they occur pretty frequently. And let me start this way. Okay, so here are the derivatives of the inverse tangent and the inverse sine and their chain rule counterparts, right? We said of the 6 inverse trig functions, these are the two most important because of the frequency with which they occur. But again, consider this. I want to take the derivative of this function. Notice that the argument is the variable x divided by the constant a. And out in front, you've got the constant 1 over a. All right, so I'm going to need the chain rule to take the derivative of this, but that's okay. I'm going to set 1 over a, the constant in front, I'm going to set that aside. But otherwise, using the formula above, the derivative of the inverse tangent is the derivative of the argument, which in this case is 1 over a, divided by the quantity of 1 plus the argument squared. All right, now I'm going to clean that up. All right, and when I distribute across the denominator, I get the expression okay? See how that simplified really nice? And so what this implies then okay? Now, the reason I point this out is because these kinds of things occur pretty frequently, right? These kinds of integrals, just like the derivatives occur frequently, so do the antiderivatives, right? Here's a couple of examples. All right, so here we see that the letter A in this case takes the place of 2, right? Because 2 squared is 4. And so therefore, by the result that we just found above, okay, allows us to go right to the answer. It's worth memorizing, gang. I would say it's worth memorizing because it occurs pretty frequently. All right, so we'll modify it a little bit. Yeah? Actually, you know what? Let's do this. Let's factor the 4 out of it. Now, 4 in the denominator, I'll set it aside. And then I'll use the property of exponents. Now, it's got the inverse tangent form to it, gang, but notice that the expression 3/2 x, right? What do I need in the numerator? Okay, let me remind you. Let me go back up here. Okay, remember, the derivative of the inverse tangent of g of x is equal to its derivative divided by 1 plus g of x raised to the second power. In other words, gang, the numerator has to be the derivative of this function before you square it. Okay? All right, let's go back to our problem. Okay, what do I need on our numerator here? Yeah, good. We need a 3/2. All right, so let's multiply by 3/2 and 2/3 out in front to compensate. All right, we can go right to our answer. And of course, we can simplify that a little bit, yeah? Okay, how does that look? All right, good. Now, this doesn't look like an inverse tangent at all, right? You've got that middle term, 4x there, okay? We do not have a chain rule. One part is not the derivative of another part. In particular, the numerator is certainly not the derivative of the denominator. So we're not even looking at the result of taking the derivative of a logarithm, okay? Remember, we've said, and we maintain this, sometimes you have to be clever when solving integrals, right? So here's one way that we can be clever. I'm going to borrow 4 from the 5. Like this. Okay, see how I rewrote the 5 as 1 plus 4, right? 1 plus 4. And the reason I set those 3 terms off to the side like that in a grouping, gang, is because I recognize that that is a perfect square trinomial. In fact, it's equal to the quantity of x plus 2 squared. Okay? Now that is highly suggestive of our inverse tangent. We just have to make sure that the numerator is correct. What do we need in the numerator for this to be a perfect inverse tangent? Yeah, we need the derivative of x plus 2 in the numerator. What is the derivative of x plus 2? Yeah, good. It's 1. And you've got the 1 already. Very good. And so we know we can go right to the answer then. You may make a note, gang, that right over here, a would take the place of 1, right? 1 squared is equal to 1. And I'm going to say similarly, we can show by the same way that we did for the inverse tangent. Notice this one does not have the extra factor of 1 over a out in front of it, okay? And gang, I encourage you to take the derivative of the right-hand side and simplify it and show that you will get the original integrand. Okay, what is a in this case? Yes, good. It's the square root of 5. Good. A is the square root of 5. Okay, so 2 special integrals, okay, 2 useful integrals to be sure, worth memorizing.